Good afternoon to respected Dr. Tina ma'am and my fellow classmates present here. This is Vivek Hotti, roll number 32, and today, along with my fellow team members, I am going to present the topic orthonormal set of functions under the kind guidance of Dr. Tina ma'am. Firstly, let's glance over our group members and their roll numbers. Now, moving on, let us first understand what is meant by orthonormal functions. It is a set of functions starting from f1x, f2x, f3x until fnx is said to be orthonormal over an interval of a comma b only if integral of the product of fmx and fnx over an interval of a comma b dx either is 0 if m doesn't equal n or equals 1 if m equals m. In other words, we paraphrase the above statement by stating integral of fmx multiplied by fnx dx equals to 0 if m doesn't equal n, and integral of fnx the whole squared dx equals to 1 if m equals n. Now, moving on, let us understand the difference between orthogonal and orthonormal functions. Fmx and fnx is said to be orthogonal only when they satisfy the condition integral of a to b fmx multiplied by fnx dx equals to either 0 if m does not equals to n or doesn't equals to 0 if m equals to n. Whereas, on the other hand, as we saw in the case of orthonormal functions, fmx and fnx are said to be orthonormal only if the integration of the product of both these functions over the interval of a comma b is equals to 0 when m doesn't equal n or equals to 1 when m equals n. The textbook definition of orthogonal functions is that orthogonal functions belong to a function space which is a vector space that has a bilinear form. Whereas the textbook definition of orthonormal function states that two vectors in an inner product space are orthonormal if they are orthogonal and unit vectors both. Next up, you could see the pictorial representation of both the types. In orthogonal, the functions are compulsorily supposed to be perpendicular to each other, while on the other side, in the case of orthonormal, we see that in addition of functions being perpendicular to each other, they are also unit vectors, that is the value of each function is 1. With these observations, we conclude that every orthonormal set of function is compulsorily orthogonal. Now, I would like my friend Dhruv Shah, role 105, to continue to enlighten you more on this topic.
Good afternoon, all. My name is Dhruval Shah, and I'm going to talk about the general concept and how Fourier series is related to orthonormal set of functions. So, starting with general concept, an orthonormal basis is a set where the elements are orthonormal and form a basis. So, a basis is an entity which is used to define a vector, and we know what are orthonormal elements from the previous slides. Thus, every suitable function f can be uniquely expanded as a linear combination of a basis set element. For example, I cap, j cap, k cap is used for three-dimensional space. The same way I cap and j cap can be used for two-dimensional space. Now, talking about the relation of Fourier series with orthonormal basis, a Fourier expansion or Fourier series is an expansion of function in terms of orthonormal basis or of complex exponential. If not complex exponential, it can be also a trigonometric function. This corresponds to a specific choice of orthonormal basis. There are others present as well. The complex exponential corresponds to the eigenstate of the momentum operators in free space or a particle in a box, the energy eigenstate. Now as we know about the basic concept and the relation, we going to move on to the numericals.
Good morning to one and all good afternoon to one and all present. I, Rohan Makwana, serial number 52. I'm going to take you through the first numerical of this interesting topic. The question of the first numerical is as follows. If f of x is equal to c1 phi 1x plus c2 phi 2x plus c3 phi 3x, where C1, C2, C3 are constants and phi1, phi2, phi3 are orthonormal functions on a comma b, show that definite integration from a to b of f of x square dx is equal to c1 square plus c2 square plus c3 square. So let's understand this question. We have been given a function of x which is equal to summation of multiples of functions of x, where phi1x, phi2x, and phi3x are orthonormal on a comma b, and we have been also given that c1, c2, c3 are constants, and we have to prove this given equation. So let's start with the solution. Since phi1x, phi2x, and phi3x are orthonormal, it means the conditions for orthonormal will be valid on them. So we'll go on with the first condition when m is equal to n. Here, as both the functions are same, we'll take the square. So it corresponds as definite integration from a to b of phi1x square dx is equal to definite integration from a to b of phi2x square dx is equal to definite integration from a to b of phi3x square dx is equal to 1. Let it be result number 1. Also, we can apply the second condition when m is not equal to n. Here, as m is not equal to n, we can write it in a generalized form as definite integration from a to b of phi mx into phi nx dx is equal to 0. We will come to result number 3 in a short while. Let's start by solving. Let's start by taking the LHS of the equation. LHS of the equation is equal to definite integration from a to b of f of x squared dx. We have been given the value of f of x. We'll just substitute it over here, and it would become definite integration from a to b of c1 phi1x plus c2 phi2x plus c3 phi3x the whole square. If we observe we are getting a plus b plus c the whole square identity. So what's a plus b plus c the whole square? It's equal to a square plus b square plus c square plus 2ab plus 2bc plus 2ac. So we'll expand it accordingly. Here a is equal to c1 phi1x, b is equal to c2 phi2x plus, and c is equal to c3 phi3x. On expanding, we get c1 square phi1x square, which is in place of a square, plus c2 square phi2x square in place of b square, plus c3 square phi3x square in place of c square, plus 2c1 c2 phi1x phi2x in place of 2ab, plus 2c1 c3 phi1x phi3x in place of 2ac, plus 2c3 c2 phi3x phi2x in place of 2bc. As we know, c1 c2 c3 are constant. We can take them out of the integration. So the following step becomes c1 square definite integration from a to b of phi1x square dx plus c2 square of definite integration from a to b of phi2x square dx plus c3 square definite integration from a to b of phi3x square dx plus 2c1 c2 definite integration from a to b of phi1x phi2x dx plus 2c1 c3 definite integration from a to b of phi1x phi3x dx plus 2c2 c3 definite integration from a to b of phi3x phi2x dx. Now, as from results 1 and 2, we know that definite integration from a to b of phi1x square dx is equal to 1. Similarly, definite integration from a to b of phi2x square dx is equal to 1, and definite integration from a to b of phi3x square is equal to 1, as we can see in result number 1. We can also see that the definite integration from a to b of phi1x phi2x resembles our result number 2. So the value becomes 0. Similarly, this definite integration from a to b of phi1x phi3x dx also becomes 0, and definite integration from a to b of phi3x phi2x also becomes 0. So we are left with c1 square into 1 plus c2 square into 1 plus c3 square into 1 plus this entire things becomes 0, which will on simplification we will get c1 square plus c2 square plus c3 square, which is what we needed to prove. Hence we have proved that definite integration from a to b of f of x square dx is equal to c1 square plus c2 square plus c3 square. Now my friend Yash Dave will continue with the second numerical.
Thank you, Rohan. Good afternoon, everyone. Yash Dave here. I am here to explain one of the sum on orthonormal set of function in Fourier series. So, question is: consider the interval I equals to 0 to 2 pi, and we need to prove that system of function where n belongs to 0, 1 to till infinity is orthonormal on I. Here, n belongs to 0, 1 to till infinity, then the function e raised to inx by root 2 pi, comma e raised to nx by root 2 pi is equal to definite integral of 0 to 2 pi e raised to nx by root 2 pi into e raised to nx by root 2 pi bar dx. We all know that e raised to I theta is equals to cos theta plus I sin theta. So, and here theta is equals to nx. So we will get integral of 0 to 2 pi cos nx plus I sin nx by root 2 pi into cos nx minus I sin nx by root 2 pi dx. Now we will multiply it and we will get integral of 0 to 2 pi cos square nx minus I sin nx cos nx plus I sin nx cos nx minus I square sin square nx by 2 pi dx. Here, I sin minus I sin nx cos nx plus I sin nx cos nx gets cancelled and we get integral of 0 to 2 pi cos square nx plus sin square nx by 2 pi dx. We all know that cos square theta plus sin square theta is equal to 1 and here theta is equals to nx. So we will get integral of 0 to 2 pi 1 by 2 pi dx and here 1 by 2 pi is constant, so we will take it out from the integration, which will be given 1 by 2 pi integral of 0 to 2 pi 1 dx. Integration of 1 dx is equal to x dx, and by putting upper limit minus lower limit, we will get answer as 2 pi by 2 pi, which is equal to n. And here we have solved the case 1 where m is equal to n. Now for case 2 where m is not equal to n, m comma n belongs to 0, 1, 2 till infinity, and we have assumed m greater than n. Then function e raised to nx by root 2 pi, comma e raised to nx by root 2 pi equals integral of 0 to 2 pi e raised to I mx by root 2 pi into e raised to I nx by root 2 pi bar dx. Further, e raised to I theta equals to cos theta plus I sin theta, and here theta equals to m comma n. So we will get integral of 0 to 2 pi cos mx plus I sin mx by root 2 pi into cos nx minus I sin nx by root 2 pi dx. Now we will multiply it and we will get integral of 0 to 2 pi cos mx cos nx minus I sin nx cos mx plus I sin mx cos nx minus I square sin nx sin mx by 2 pi dx. Now we will separate the real part and imaginary part and we will get definite integral of 0 to 2 pi cos mx cos nx plus sin mx sin nx by 2 pi dx plus I integral of 0 to 2 pi cos mx sin nx plus sin mx cos nx by 2 pi dx. By solving it further, we will get this function, this equation is equal to 0. And from this to from case 1 and case 2, we will come to know that e raised to nx by root 2 pi, comma e raised to nx by root 2 pi bar is equal to 0 and it's orthonormal on the interval I 0 to 2 pi. Now I urge Arshita to carry forward the presentation. Thank you.
A very pleasant good afternoon to one and all present over here. This is Harshita Srivastav, roll number 118 from Comms Department, and today I am going to explain the sum on the basis of orthonormal set of functions. According to me, this is a very simple concept which will help you to distinguish between orthogonal and orthonormal set of function by solving this sum. So let's move ahead. So the question begins, so that the set of function that is sine pi x upon 2l, sine 3 pi x upon 2l, sine 5 pi x upon 2l, and so on is orthogonal over limit 0 to l, construct corresponding orthonormal set of functions. So the solution begins as, for sine set of functions, we use fnx is equal to sine 2n plus 1 pi x upon 2l, where n ranges from 0, 1, 2, 3, and so on. Further, we will be proving these two cases. Case number 1. Integral from a to b fmx dot fnx dx. Now, as we know the limit is from 0 to l, therefore, by applying the limit, we get integration 0 to l sine 2n plus 1 2m plus 1 pi x upon 2l dot 2n plus 1 pi x upon 2l dx. Now, as we all know the formula for trigonometric equation, we will be multiplying and dividing it by 2. So what we get is 1 by 2 into 0 to l limit from 2 sine 2m plus 1 pi x to l upon sine 2n plus 1 pi x to l dx from the formula, that is 2 sine a sine b, which is equal to minus cos a plus b plus cos a minus b. Now, further solving that particular expression, what we get is 1 by 2 ranges from 0 to L minus cos 2m plus 1 pi x upon 2L plus 2n plus 1 pi x upon 2L plus cos 2m plus 1 pi x upon 2L minus 2m plus 1 pi x upon 2L dx. Now, on the right hand side of the sheet, we get 1 by 2 0 to L minus cos 2m plus 2n plus 2 pi x upon 2L plus cos 2m minus 2n pi x upon 2L dx. Further, we get 1 by 2 minus sine 2m plus 2n plus 2 upon 2L into pi x plus sine 2m minus 2L pi x upon 2L from limit 0 to L. Now, for solving further, what we get is 1 by 2 minus sine m plus n plus 1 pi by taking out 2 common plus sine m minus n pi minus 0 comma 0. How this came? As we have applied some limit into it. And as we all know, the value of sine n pi is 0 in maths. Therefore, the kind of equation which we get from this is 1 by 2 0 minus 0 is equal to 0, which means that m is not equal to n. Therefore, it satisfies. Further, what we get is the equation by doing the case number 2, that is integration from a to b fmx the whole square dx is equal to integration of 0 to L sine 2m plus 1 2n plus 1 pi x upon 2L the whole square dx. Now, by solving at the formula of trigonometry, we can say that cos 2x is equal to 1 minus sine square x. So, by transposing sine square x, what we get is 1 minus cos 2x by 2. Now, further applying that particular part in that question, we get the sum as integral part from 0 to L 1 minus cos 2 into 2n plus 1 pi x upon 2L upon 2 dot 2x. Now, further solving that given integration, what we get is 1 by 2 x minus sine 2 into 2n plus 1 pi x upon 2L dot 2L upon 2n plus 1 pi x into ranges from 0 to L. Now, this 2L upon 2 into 2n plus pi x is obviously the reciprocal, so that it can cancel out very easily. Now, after solving this particular expression by cancelling each and every term, the main answer which we get is 1 by 2 L minus 0, which is nothing else but L by 2, which is not equal to 0. Therefore, we can say m is equal to n. So, the given set of function is orthogonal. Now, as we all know, the constant term which we got is L by 2. So, for making it a construction for orthonormal set of function, what we'll do is we will divide and multiply the whole equation by L by 2 on both the sides of the equation. So, from that, what we will get is integration from 0 to L sine square 2n plus 1 pi x upon 2L dx is equal to L by 2. Now, further solving that equation by keeping L by 2 on both the sides, we'll get is integration limit from 0 to L sine square 2n plus 1 pi x upon 2L dx upon L by 2 dx is equal to L by 2 upon L by 2. Now, further solving that equation L by 2 upon L by 2, we get 1. So, basically, the kind of equation which we get by applying root and all is limit from 0 to L into root 2 upon root L sine into 2n plus 1 upon 2L pi x upon L by 2 into 1 dot dx is equal to 1. Therefore, the orthonormal set of function is given by root 2 upon root L into sine 2n plus 1 pi x upon 2L. Here we came to conclude that the main construction of orthonormal set of function which we need is root 2 upon root L into sine into 2n plus 1 pi x upon 2L. Now I would request my friend Dhruv Sonani to explain this further. Thank you.
So good afternoon to one and all present here. Myself Dhruv Sonani, roll number 117, going to start with fourth sum. Example number 4. Show that the function sine 2n plus 1x are orthogonal over 0 to pi by 2 and also construct an orthonormal set of function. Basically, this example is based on orthogonal and orthonormal function and it is very important from exam point of view. So without wasting your time, let's start this sum. The function fnx equal to sine 2n plus 1x where n equal to 0, 1, 2, so on. Duplicate function fm x equal to sine 2m plus 1x where m equal to 0, 1, 2, 3, so on. So now we will split this sum into two parts, that is A orthogonal and B orthonormal. So in orthogonal, the function is given as integration 0 to pi by 2 fmx into fnx dx. So now putting the value of fmx and fnx, we get integration 0 to pi by 2 sine 2m plus 1x into sine 2n plus 1x dx. As we know, sine A sine B equal to cos A minus B minus cos A plus B. So by applying this formula, we get half integration 0 to pi by 2 cos 2m plus 1x minus 2m plus 1x minus cos 2m plus 1x plus 2m plus 1x dx. By removing a common, we get half integration 0 to pi by 2 cos 2m plus 1 minus 2m minus 1x minus cos 2m plus 1 plus 2m plus 1x dx. Now by rearranging the equation, we get half integration 0 to pi by 2 cos 2m minus 2nx minus cos 2m plus 2n plus 2x dx. By integrating this equation, we get half sin 2m minus 2n x upon 2m minus 2n minus sin 2m plus 2n plus 2 2m upon 2m plus 2n plus 2 with limit 0 to pi by 2. Now by applying the limit 0 to pi by 2, we'll get the final answer 0. Hence the function are orthogonal. So now we will start the second part, that is orthonormal function. So in orthonormal, the function is given as integration 0 to pi by 2 fnx into fnx dx. By putting the value of fnx, we get integration 0 to pi by 2 sine 2n plus 1x into sine 2n plus 1x dx. By combining these both, we will get integration 0 to pi by 2 sine square 2n plus 1x dx. As we know, sine square x equal to 1 minus cos 2x by 2. So by applying this formula, we get integration 0 to pi by 2 1 minus cos 2 2n plus 1x dx by 2. Now by removing the constant outside, we will get half integration 0 to pi by 2 1 minus cos 2 2n plus 1x dx. By integrating this equation, we will get half x minus sine 2 2n plus 1x upon 2 into 2n plus 1 with limit 0 to pi by 2. By applying this limit to this equation, so we'll get the answer 1 by 2 into pi by 2. By solving this, we will get the final answer pi by 4. So now as we are doing orthonormal, our right side of this equation must contain 1. So to get 1 on the right side, we have to divide pi by 4 on the both side of this main equation. So integration 0 to pi by 2 sine 2n plus 1x into sine 2n plus 1x dx divided by pi by 4 equal to pi by 4 by pi by 4. So it is an orthonormal function. We have to split pi by 4 into two parts. So our equation will be integration 0 to pi by 2 sine 2n plus 1 x into sine 2n plus 1 x dx upon under root pi by 2 into under root pi by 2 equal to 1. So our new function will be 2 upon root pi into sine 2n plus 1 x where n equal to 0, 1, 2. Hence we have proved that it is an orthonormal function. Thank you. I would like to call Vivek Hoti to continue the next topic, that is application.
Thank you, Dhruv. Let us now focus on the applications of orthonormal functions. It's a matter of fact that the range of real-life uses and applications of orthonormal functions are very limited. The Gram-Schmidt process, although, is the only most significant application of orthonormal functions. Gram-Schmidt process is a method for orthonormalizing a set of vectors in an inner product space, most commonly the Euclidean space. Euclidean space at first seems to be a complex word, but it's a 2D or 3D space where points are designated by coordinates and distance between 2 points is given by the distance formula that we have studied in grade 10. Now, coming back to Gram-Schmidt process, this process takes a finite linearly independent set. S is equals to V1 until Vk for k is less than or equals to n and generates an orthogonal set. S dash is equals to U1, U2 until Uk that spans the same k-dimensional space of Rn as S. Now with this, we come to the end of our presentation. Thank you one and all for being a great audience.